Hello. In the last lecture we covered binary search trees and compared them to sorted arrays and went through a few of their operations. And today we're going to go over red-black trees, which is a type of binary search tree that's balanced. So it maintains that property that all these operations that depend on the height of the tree will be sort of optimal. Why are we talking about red-black trees? Well, they're a little bit out of date in terms of something that you would want to use in your code, but they're just a really good choice for showing you the different ways that you can play around with properties and invariants and end up with what you're looking for. And they are still used. So in fact, the Java tree map and in C++ the stud map are both red-black tree implementations. All right, so let's start by remembering why balancing is important. What's the worst case in terms of balance for a binary search tree? It's a tree where all the nodes sort of go down one side or zigzag back and forth. And if you remember, the height of the tree, of a balanced tree, stays roughly big O of log n after insertions and deletions. And that's important because most operations are going to take, worst case, whatever the height of the tree is itself. And there are a lot of different types of balanced trees. There are AVL trees, splay trees, B trees. There's a few others. And what we'll talk about in these slides is red-black trees because they're sort of an interesting academic thing to look at. And they're also, I won't say simple to understand, but it's a set of logical steps to understand them. Okay, so what is a red-black tree? It's any binary search tree that maintains these four invariants. Every node must be labeled either a red node or a black node. The root must be labeled a black node. The tree cannot have two red nodes in a row. So that means for any red node, its parent and its left and right children both must be black nodes. And every single root to null path must include the same number of black nodes. So let's dig into these properties and see what they mean. Well, first, I have a question, which is, can a red-black tree of any height have only black nodes? And the answer to that is yes, and we will see why in just a few slides. All right, so let's look at our first tree and see if it can be labeled as a red-black tree. And we'll call this a chain because it has three nodes in a row. And for the next few slides, I'm going to explicitly show the nulls just so every root to null path makes sense. So here I've explicitly put the nulls on there. Can this chain of three nodes in a row be a valid red-black tree? Well, first we have to make sure that we color every single node red or black. We'll come back to that one. We know that the root node has to be colored black. So let me just mark that one as a black node. And it cannot have two red nodes in a row. So these two nodes here, they can't both be red. So let's try first this one as a black node and this one as a red node and see if that maintains every invariant. Well, first, everything's either red or black. The root is a black node. We don't have two red nodes in a row. But if you notice, we don't have the same number of black nodes on every root to null path. So we have 1 on this root to null path. We have 2 on this one, 2 on this one, and 2 on this one. So the fact that this one is 1 means that we've invalidated that final invariant. So let's try recoloring it a different way. We do know that the root still has to be a black node. Let's try this one as a black node and the middle one as a red node. Well, we're going to have the same problem. So I have one black node on this root to null path, 1 on this one, but 2 on both of these. So there's no possible way to color this particular structure in a tree so that it maintains the red-black tree invariance. All right, how about this one? Can we color this one as a valid red-black tree? And yeah, it turns out we can color this one to be a valid red-black tree, so let's start again. We can color the root node, and from here on out I'm going to stop showing the nulls here just so I don't have to put as many things and clutter up the slides. We can color the root to be a black node, and we can color the 3 and the 7 to be a black node so that we have two black nodes on this root to null path, 2 on this one, and then 2 here, 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 and here. So that's going through here, through there. Every root to null path has 2 black nodes on it now. Okay, so are there any other ways to color this to be a valid red-black tree? Can we change the colors of any of these nodes? And we can for this particular tree. And normally when you see a structure like this with a parent node that's also a black node, a grandparent node from the red node's perspective, that's also a black node, we can push that black color down. So we can have the 7, we can transfer its color to the 6 and 8, or really swap the colors with the 6 and 8. So now that we have this, and again, let's check. So 2 on that path, 2 on that path, 2, 2, 2, and 2. All right, so let's try one more. Can we color this one to be a valid red-black tree? And the answer again for this one will be yes. So we can color the 3 and the 7 black and the 6 red. Is there any other way to color this set of nodes so that we have a valid red-black tree? And no, there's no way to move the colors around. So, for example, if we were to swap the colors of these two nodes and make this one red and color this one black and count the number of black nodes on every path, we'd have 2, 2, 2, 2, but just 1 this way. And we certainly can't color this one to be red. So if we colored that one red, that means there can only ever be one black node on any path, which means we'd also have to color this one red. But now we've invalidated invariant 3, that we can't have 2 red nodes in a row.